In this video, we present the retrosynthesis of pentadeuterate ethosuximide, a deuterated drug that can be useful in researching the pharmacology and metabolism of this antiepileptic drug, as well as a reference standard for bioanalytical methods. The retrosynthesis of this pentadeuterate drug begins with disconnections based on amidation reactions to generate deuterated diethylsuccinate as the first precursor. Subsequent transformations produce the disubstituted diethylmalonate with a deuterated ethyl chain as the next key precursor. It should be noted that the deuterated chain comes from acetylene and deuterated water as the source of this isotope, as we will see later. The amido group in the heterocycle present in 1 acts as a retrone, and a first carbon-nitrogen disconnection, based on an amidation reaction, opens the ring and produces precursor 2. A second carbon-nitrogen disconnection leads to disubstituted diethylsuccinate 3 and ammonia 4 as raw material. The disubstituted succinate on the same carbon atom suggests its formation from a symmetric compound to avoid regioselectivity problems in alkylation reactions. With this idea, a functional group transformation leads to compound 5 with a nitrile group. A carbon-carbon disconnection in 5, based on a nucleophilic substitution reaction, generates the iodinated compound 6 and sodium cyanide 7 as raw material. Another functional group transformation leads to the primary alcohol 8, which through another functional group transformation generates the disubstituted malonate 9. With these transformations, we reach an intermediate where the following retroreactions do not present regioselectivity problems. A carbon-carbon disconnection in 9 produces the monosubstituted diethylmalonate 10 and the pentadeuterate ethyl iodide 11. A carbon-carbon disconnection in 10 generates diethylmalonate 12 and methyl iodide 13 as raw materials. A functional group transformation yields perdeuterate iodothane 11 from perdeuterate ethanol 14. Another functional group transformation gives rise to perdeuterate acetaldehyde 15. A functional group transformation based on a hydration of a triple bond with deuterated water produces the dideuterated acetylene 16 as the next intermediate. Finally, the deuterium atoms in 16 can be incorporated from ionized acetylene 18, which arises as a raw material when reacting with deuterated water, which arises also as a raw material and source of deuterium. In summary, the main disconnections are shown here. The resulting synthesis will be presented in the next video.